There is a demonstration out in the lobby during lunch. A couple of wonderful women are going to be showing you examples of using this sort of data, so check that out during the lunchtime. Thank you, Karen. So she talked about geological disturbance, so kind of the underground stuff you should know about, and I challenge you all to go home and hug your soil scientist if you haven't done that before. Paul Hessburg is going to talk about disturbances basically on the surface of that geology. Paul is a research landscape ecologist with the PNW Research Station, and he's going to bring in climate, environment, fire history, disturbances, and all that other kind of messy stuff on the planet's surface. So help me welcome Paul Hessburg. Messy stuff.
Good morning. I'd like to thank the planners for including me in the agenda. Like Cheryl said, I'm a landscape ecologist, and I study how patterns on the terrestrial landscape drive processes and how processes are actually driving patterns. So the crosstalk between pattern and process is what I dwell in. And I wanted to underscore one of the ideas that Karen mentioned about mollisols. We found mollisols are such an amazing predictor of the grass fire cycle that when we look at the overlay of mollisols throughout the interior, we see that about 80%, depends on the province, but about 80% of it was so much of a grassland and driven by a grass fire cycle that it didn't make forest cover definition. It would be a sparse woodland in the ponderosa pine PVT, about 8 out of 10 acres, really underscoring that the dominant fuel over millennial time depths was grass, and it was a grass fire cycle dominating. But what I'd like to do in the time that's remaining here is I would like to talk about how climate, environment, and disturbance history work together to govern not only the resilience but also the resistance of a landscape. We know that the Pacific Northwest has undergone an awful lot of changes, and I'm not going to do a deep dive into it because we've all been reading about it for the last 30 years. But the changes are really quite significant, and they help us to focus on not only where we've come from, but where we need to go as a consequence of changing wildfire regimes and climate change. I want to focus my comments first on some of the inland forests. We've been studying these for the last 3 decades or so, and the changes are incredibly dramatic. We've seen that grasslands and shrublands and sparse woodlands have decreased, and forests have encroached on many of those. Many landscapes have actually flipped to become forest-dominated where they were not. Dry slopes and ridgetops have filled in with trees, so the topographic and soil mosaic that would have really been influential on that landscape has shifted, and it's hard to see that template nowadays. Complex forest successional patchworks in the inland have become really uniform in this interval when we've excluded fire. And so we're literally not seeing how burn scars created pattern and process over space and time. Patchworks of burned and recovering forest, they gave way to continuous forest. One of the things I want you to see in that upper photo is just how much fire was on that landscape, and that wasn't extraordinary. There are many landscapes that looked like this when we inherited these forests some time ago. Fire was a really prominent part of the landscape. Abundant meadows gave way to dense forest. This is in the Blue Mountains. These are elevations 7,500 and 9,000 feet. And what I want you to see here, it's not just in the dry forest. There's a huge loss of wet and dry meadows, and in many areas we've seen a 10 to 1,000-fold or 100-fold increase in the number of trees. So forest area has increased significantly, and forests have become denser. And it's not just in the mixed conifer zone. There have been a lot of changes and a lot of change agents. And again, I'm not going to do a deep dive, but this is the commingling of factors over 100, 150 years that produced really significant influence on our landscape. And it begins with the loss of cultural burning. And climate change, at the bottom of the list, is really ramping up how these factors have worked together to change the landscape, and now how climate change and associated wildfires are threatening to provide influence. But one thing we don't often think about is that changes in the terrestrial landscape and in the fire regime have radically affected the aquatic ecosystem. If you stop and think about it, if forest area increases and tree density gets greater, then the landscape has been dewatered as a consequence of expansion of forests. Trees are pumps, and we're now looking at that in a number of different research grants, and we're finding out that the change in snow interception, the timing of snow melt, the release of snow water is hugely affected by the changes in the forest. Hill slope processes that were driven by the fire regime, that rhythm, that pulsed rhythm of fire frequency and spatial extent. When you keep that out of the woods, you change hill slope processes, which are essential for aquatic habitat succession. So I'd like to challenge you to think that these changes have not only influenced terrestrial landscapes, but aquatic landscapes. And there really is no division between the terrestrial and the aquatic landscape anymore. They talk to each other, and they used to have an amazing conversation. This is also true of many West Side forests as well. This is the controversial Eagle Creek landscape in the Columbia Gorge. We're looking at it from Dog Mountain, Washington. We're looking across at a history of overlapping burn scars over space and time. So the landscape we inherited early 20th century in that area was that landscape right there, and none of us remember it. And so when we saw Eagle Creek happen, we thought it was a disaster. But it actually was so much less fire than that landscape historically had on it. Also in West Side Forest, we've recently completed the Northwest Forest Plan science synthesis, and we've reconfigured fire regimes pretty significantly on the west side. And so I want to drill down into the fire ecology and some of the landscape ecology of the Coast Range and the West Slope. You can see in this map here that we have changed an awful lot of the West Slope fire regime from being completely standard placement or high severity to both low and moderate severity, and those two actually occupy a greater space than the high severity regime. Let's drill into that a little bit. In Chapter 3 in that science synthesis, we basically break down what those fire regimes look like. And we identified 4 paths, basically, and you can think of those as sort of schematics or ways of thinking about fire in concept. The first 3 are high severity regimes that result in periods of grass and shrub cover, and it takes 5, 6 decades to get into a stem exclusion closed canopy Doug fir, which is then followed by the Doug fir hemlock mix. Or you'll see a much longer period of grass shrub, or you'll see grass shrub yielding to alder for 100, 120 years, and then encroachment of Douglas fir on that. And in Path D, you see a mixed severity periodic regime where you actually have patchy, gappy Douglas fir with inclusions of Douglas fir hemlock, and this is self-repeating over space and time. When we drilled into that even further, considering John Tepley's work, again, thinking about the area that's in brown, red, and blue on that map, we find that in the intervals between standard placement fires, there was a lot of fire on the landscape, and that fire on the West Slope created a varied patchwork of successional conditions. And that varied patchwork of successional conditions was morphing over space and time, and mixed and high severity fire were driving that successional patchwork. And that successional patchwork included non-forest. It was a part of the recipe on the landscape. Okay? So one idea that I want you to consider is that the West Side forests and the coastal forests are not asbestos, but they had a fire regime, and it's coming back to the west slope, okay? Haugo et al., I want to consider that work for a minute. What they did is they basically said, well, if we've missed fire on the west slope, how much fire did we miss? And what they do is they use a similar map of fire regime groups. Fire regime group 1 is generally low severity. Group 2 is not indicated on this map. It's the former grasslands in the Columbia Plateau and other areas of the Basin and Range. Fire regime 3 is mixed severity, 4 is high severity fires, and 5 is a mix of severities, but it's mostly dominated by replacement severity fires. And one of the things that they found out is that there's an order of magnitude less fire on the west side than there was historically. And here's how they broke it out. What they basically found here is that there was much more burned area at any time of all fire regime types historically. So every single fire regime group was affected significantly by fire exclusion. When they considered the observed versus expected proportion of fire, what they found out is that the system is flipped. It's not functioning at all like it used to function. There's currently less low severity fire and more mixed and high severity fire in the low and mixed severity fire regimes, and the converse is true in the high severity fire regimes. So it means we're hooking fires, and they're not being severe enough and extensive enough in the high severity regimes, and we're simply not getting enough fire in the low and mixed severity fire regimes. So those are comparisons with historical fire regimes, but our goal is to climate change and wildfire adapt this landscape, isn't it? It's not to go back to history, and if you stop and think about it, our study of historical variation is not the goal. It literally is the set of breadcrumbs we followed to find out that there was variability in the system, and it could be captured and it could be understood. But that variability is constantly evolving, and it's very rapidly evolving right now under climate change. So what does climate change hold for us? I want to show you a couple of movies here. This is the energy release component that we've calculated for ERC 55 days. These are for weather years 1980 to 2018, and these are days when wildfires are able to ignite within Oregon and Washington. So you can see that they're everywhere they're able to ignite within Oregon and Washington, but some places really are hot spots. So these are places where fires are available to burn, fuels are available to burn, and they're available to go. This is a look at ERC 67 plus days for a standard fuel model. These are days when if you get an ignition, you're likely to result in a problem fire that escapes initial attack, okay? And my personal favorite, this annual SPAY index basically takes a look at the push-pull between precipitation and potential evapotranspiration. And what it's basically telling us is each year, who is the winner between the amount of incoming precipitation and evapotranspiration. And you can see in many years, there's no difference between the west side and the interior. And in some years, the west side is actually drier than the interior is. What does that mean? This index is really helping us to understand two things pretty clearly. One of them is die-off events that we're experiencing and where they occur. We're seeing western red cedar and hemlock and Douglas fir die off in plantations and young forests, aren't we? Well, this index helps us to understand what kind of stress they're under. It also helps us to understand this new idea of flash droughts. We may be getting the snow and the precipitation in the system, but we're getting these weather patterns, these blocking ridges of high pressure, right, that are causing our fuels to become available in 3, 4, 5 weeks. So we're getting basically a spontaneous and instantaneous kind of drought on the landscape. And it's a new problem we need to think about under climate change. I want to close in the moments that I have, and I want to summarize some ideas that we've captured in these two papers here. One of them is about landscape principles that we've summarized over the last 30 years, and some ideas that come from studying 15 different North American provinces, from the BC boreal zone all the way down to the Baja. There's quite a lag, isn't there? So I want to, for purposes of planning going forward, I want to emphasize that not only interior but west side landscapes are wildfire landscapes. Wildfire is a primary disturbance processes, and the patterns of both east and west side landscapes were sculpted by fire. So the fire regime is a really important rhythm to that landscape, and it creates the patterns of succession, forest succession and fuel succession that are important to those landscapes. Fire exclusion and management have changed forest successional conditions in both east and west side landscapes. Our studies suggest that fire exclusion is more important in the interior on the east side, and management is more important on the west side because of its fragmenting effects on the landscape, but both influences are still key. There's strong crosstalk between patterns of successional and fuel conditions and wildfire on the east side and on the west side. And there's an opportunity to climate change and wildfire adapt our existing conditions in both areas. We find that resilience and resistance across 15 different North American provinces has the same structure. We find that at fine scales, there are patches with clumped, gapped, or continuous trees, and these patterns are critical at a fine scale. And these nest within a mesoscale forest successional landscape. And there's crosstalk between those patterns. They provide habitat patterns, but they also influence processes at both scales. And these successional landscapes nest within broad-scale patchworks of grasslands and shrublands and sparse woodlands as well. So the non-forest is critical context to the forest as well. We find it in the boreal zone in northern BC, and the subboreal, down in the Baja, literally every area that we look at. We find that wildfires maintain patchworks of burned and recovering vegetation. Some burn scars spatially interrupt fire flow over space and time, and others facilitate it. And that's important to basically maintaining the variability of the fire regime and the successional conditions that are an emergent property of that regime. These feedbacks, this is a key point from our reburn studies. Reburns create non-forest and pre-forest. And one of the things that's important about these overlapping burn scars is that they decouple forest fuel succession from forest canopy succession. If you stop and think about it, the first fire kills the forest, the second fire comes along and reduces the dead wood, and the third fire literally moves you into a shrub and herbaceous conditions, and trees have to reinvade. So forest conditions that emerge without the dead wood component are much more asbestos than the other forest conditions. So this decoupling was a critical landscape ingredient on the landscape, east side and west side. How extensive were these conditions? Well, in the interior, we've studied it an awful lot. We've spent millions and decades, and we understand what their role is, but we understand it less so on the west side. And we have some work to do to really understand not only what that variability was, but where it's going under climate change. We need to know on the west side, for example, how to not advance the slide too quickly. We need to know how much non-forest and what kinds and what sorts of patch sizes and where did they live on that landscape. When we look at photograph after photograph, not only aerial photos, but also old panoramas and old inventories, what we find out is that non-forest was an essential ingredient, not just in the Rogue Valley and in the Willamette Valley, but interdigitated among the forests. Low elevation, mid elevation, high elevation. What did that look like on the west side? Wildfire will primarily alter forest successional conditions going forward without adaptation treatments. We can expect wildfire exclusion period is over and climate change is hastening the frequency of extreme fire weather events. So we can really expect that we're going to have wildfire as a booming agent on this landscape. We have some opportunity to direct its efforts. All right. Non-forest conditions, they provide vital context. Non-forest in some interior province was every bit as dominant as forest. For example, the Blue Mountains conditions that Karen spoke to, nearly half of that province was in non-forest, and a bunch of that was on forest-capable sites that were being maintained by a grass fire cycle. What about the west side? What do we know about that? How do we know how to sort of craft and tailor that back into the landscape under climate change? There's an interplay between ignition frequency and fire weather and forest area with high canopy cover. If you stop and think about it, if wildfire is the disturbance process, there's a tug-of-war going on between factors that are causing forests to grow and factors that are causing forests to go away. And the result of that tug-of-war varies by province and its non-forest, pre-forest, and forest conditions. This patterning we really need to come to understand on landscapes going forward. One of the things that we find out about non-forest from our modeling is that non-forest becomes a benign fire delivery system. It delivers lower energy release, shorter flame lengths, lower fire line intensity when fire meets the forest edge. So it actually ends up being a critical ingredient in the fire spread mechanism. And we know that the amount of non-forest is in flux with climate and fire weather. This interplay between forest and non-forest gives us clear clues to what we can expect under climate change. In a warmer and drier climate, we can expect less forest and more open canopy conditions than occurred historically. If the climate is cooler and moister, we reduce those extreme fire weather events. In our models, what we see is forest area naturally increases and forest density naturally increases. So it's not a static thing, it's dynamically evolving with the climate and what climate is doing to fire weather and wildfire. And regardless of these conditions, what we find out consistently is carrying capacity of forests is seldom realized. So every capable acre is normally not producing forest as a consequence of this interplay between wildfire and the climate and the forest. So this is something we can actually harness and do work with. So our science, on the science planning and management sides, I'd like to suggest that we have some work to do. We've made some considerable investments in understanding what these dynamics look like and what drives them in the interior. And I think we have work to do on the west side to similarly understand those dynamics to inform our, not only our forest planning going forward, but also landscape planning for projects as well. And I think that ends my slides. Thank you very much for your attention.
Yeah. Time for a question to Paul.
Yeah, Dee Dee.
Hi. So I've heard that the hot, dry, windy index can be related to fire starts. Is there any way that we can develop a landscape likelihood map of hot, dry, windy potential?
Can you repeat the question for us?
So Dee Dee's question was hot, dry, windy conditions basically exemplify extreme fire weather conditions. And the frequency of those conditions is going up. And you sort of can. The problem is wind flow routing and wind flow patterns are terrain driven, and when initial wind directions change or they're non-standard, they're atypical, the flow routing of fire is very, very different. It's not predicted. It's not as well predicted. So we can calculate probabilistic winds, and we always do that. But when those winds come from a novel route, everything's coming out of northwest, and then all of a sudden it's out of the south or it's out of the east, then we missed it. Yeah. Thanks.